Everyone. So I was just going through the schedule of this workshops. So I saw a lot of interesting talk that have happened even today and previous days as well. So majority of the talk was on the more focused area and in depth, and I'll be talking more on the basic front. So primarily on the recurrent neural network that you can see from my title. So I will not touch upon much of the advanced thing, but I will try to touch upon some of the basic thing, something maybe known to you. And if it is known to you, probably you can just brush up quickly. Or if you are not familiar, then probably will learn something new. So with this stuff, so let me start the presentation. So just let's look into a few examples first, then I will come to the RNN part. So let's look into this uh, two sentences. Like I went to Bhutan in 2017, or in 2017 I went to Bhutan. So both the sentence actually provides the same meaning, so which is fine. As a human being, we can understand the whole meaning. Okay. Now, if I need to build a model, or if I need to build a smart agent which can answer some kind of a query like that I have written here, when did I visit Bhutan? So then the answer is 2017, so which is very clear. But the thing is, for a smart agent or for a neural network, if it tries to find out the year, then it has to understand the whole meaning. The reason is because in one of the case, it needs to choose the last word. In another situation, it needs to choose the second word. So that is a problem because I do not know where this 2017 will appear in the sentence. So effectively, I need some kind of a mechanism, I which is independent of position, but I should be able to answer certain kinds of query. So one of the requirement here is that my model should be good enough, which is independent of the position, at least with respect to this example. Let us look into another one. Like I grew up in Bengal, and then I have few more sentences. Then something is written like I can speak fluent dash. Now, if I need to fill this dash, then probably we can guess that it will be a Bengali language. Now, the thing is, I can have a paragraph and then I can come across with this sentence. So I need to have some mechanism to store all the previous informations. So I can have a kind of a long-term dependency that I need to handle. And the length of the paragraph can actually vary depending on your input text. So that is another thing that we need to handle. Though another very interesting thing also we come across, like if you look into these two sentences, the food was good, not bad at all. The food was bad, not good at all. So these two sentences actually carry different meaning altogether, or about the food. But if you look into these two sentences, then there is a good amount of similarities, that they contain same set of words. Now the important thing is the position of the words actually matters, because I have to look into the stuff like how the words are actually placed. So the sequence of the words, how they are connected with each other, that is very much important. So so we need some kind of a mechanism which can actually model all of this stuff. So in order to do this, we try to generally use the recurrent neural network, because it has few kinds of advantages. Like it will be very good in processing the sequential data, so it can try to understand the interaction between the consecutive words, probably I can say. And the good part of the RNN is also like it can actually handle a variable length input. Like if you are familiar with traditional feed forward network or the convolutional neural network, then you will find the input length is always fixed. Like if you're using VGGNet or the ResNet, then probably your input uh, has to be in 224 plus 224 cross 3 dimension. So if you have a bigger image, probably have to rescale and then probably have to give. But RNN has that advantage. It can actually handle the variable length input. Also, the thing is, it can actually handle the long-term dependency, because for this scenario, we need to have that kind of stuff. And of course, the ordering has to be maintained, like we have looked into this stuff. Another good part for RNN is that they actually share the set of parameters over the different time step. Like if you remember the feed forward network, then you know that there will be a lot of parameters when you apply a convolutional neural network, then or the filters in the CNN, then you know the parameters are actually shared. And in case of RNN, the parameters will be actually shared across the time step. I will elaborate that stuff. So these are some kind of an advantage. And before jumping into this RNN part, one of the things we should remember, like we'll be looking mostly with the language domain. And when we process the language, we can process the language in terms of character, or we can process the language in terms of word. Now, when I have some kind of a model, let's say deep learning model, I want to feed some kind of a word and I want to predict something as a prediction. Now, the thing is, if I want to give some kind of a word, I cannot give a sequence of characters. Probably it will carry no meaning as such. So what we have to do, we have to do some kind of a embedding of the words. So one of the easiest thing that we can do a kind of a one hot encoding, or we can actually use some kind of a word embedding. I will not go into that details. Only thing that I wanted to mention that, so if I want to provide some kind of a word, this word will be converted into some kind of a vector form, and then this numerical value will be given as an input to the actual model, and then probably it will predict the stuff. So now, coming to different kinds of problem that we face in the language domain. um, so one of the thing, or the different kinds of networks that we need to handle. So feed forward network is quite common, that probably you have seen, like if you want to predict something like the basic classification problem or the image classification problem, you will have a feed forward network. Maybe you can have CNN kind of architecture in between, but it will be mostly directed acyclic graph, that probably I can say. Now, if you look into the other kinds, the different problems that are available, like if you look into this kind of problem, image captioning, so you give input as one image, and you try to predict a few set of words for that image. So it's not just a single output, but your output can vary depending on the image. So the output is somehow not a fixed length for all images. So that is one of the things that we have to handle. In case of feed forward, for every input I have just a single output. For when we look into this language domain problem, I can have different kinds of configurations. So image captioning is one of them. If you look into the sentiment analysis, like you are given a paragraph, whether the paragraph is of positive sentiment or it's of negative sentiment, so that we have to analyze. Now here, the input will be the set of words on the review or some kind of a text, and by looking into all the words I have to predict either yes or no. So it will be a kind of a classification, but the input can actually vary. So effectively here, it's a one to many kind of mapping. Here I have many to one kind of mapping. So somewhat inverse of this image captioning. If you have a problem, like if you want to label every frame of the video, then you will have a kind of a dependency across the frames, and for every frame you will be predicting something, some kind of a output, some kind of a labeling. So it's many to many kind of mapping. And another kind of mapping also can come into the picture, which is many to many, but the thing is it's kind of a staggered or skewed. Like if you look into the language translation problem, so I want to translate some text from English to Hindi, then I look into the whole English statement and then I start generating the tokens for the Hindi or the words for the Hindi statement. So unless I look into the whole stuff, I will not be able to generate the correct set of meaning. So effectively once I look into the whole text, then I will be able to generate the stuff. So it will be, it's kind of a many to many, but it's kind of a staggered one. So this kind of problem we need to address when we look into the language domain problem. So so how we actually do all those stuff, so I will elaborate with a very simple stuff, because it has a proper mathematical thing. So I may not go very deep into the maths, but I will try to give a rough overview of the whole thing. So so let's say let us consider a simple situation. Let's say I want to predict the next word, which is the situation. So I have seen some of the text, some of the words, and then I want to predict the next word. So, so let's say I have some model, probably which can actually predict the next word in a very simple sense. I have looked into all the words till now, and let's say I have set up some parameters based on which I am doing the prediction. So if I know some kind of a prediction up to t minus 1, I take the prediction from t minus 1. So prediction at t minus 1 and the set of parameters, and then I predict the next word. Then again, this word will be the new word, and I'll be using the same set of parameters and same set of function. Again, I'll be predicting is t plus 1. So one of the thing is I'll be reusing this function. I'll be every time I get some kind of a output or I get some kind of a input, I apply f, and then I predict the next word. And every time I will have the same set of theta parameters. So over the time step, my theta will remain fixed. So the set of theta parameters will not vary across the time step. So this is a situation when I try to combine, or whatever history that I have, I try to combine the whole history into a single information. So that is the main point to take from this slide. So whatever history I look, I summarize the whole history and I put it into the next state, something similar to your finite state machine. So the next state will depend only on the previous state, because if we try to keep the whole history, then the history can be too long to remember. So this is the step. So maybe let's look into this example. So let's say I have some kind of a system which takes one input at a time, and then probably it predicts something. So when I have this recurrent neural network, probably I can represent it in a very concise form. I have this input and I have some kind of a state, and there is a kind of a feedback loop within the state. Now, when I actually unfold the system, I'll be getting a picture something like this on the right hand part. So I have some initial state, I take the input, I apply my function f, I reach to a new state. Then I apply my function f, I take the next input and I reach to a kind of a new state, and so on and so forth. So the interesting thing here to note, like I'll be applying the same set of function over the time step. These all f's are actually equal. The weight parameter that I have not shown here in the picture, so that will also remain fixed. So now, if we try to predict, let's say ht, so then it basically depends on ht minus 1, the current input, and set of parameter theta. And if you look this theta, then theta is independent of time. So at every time step, my theta will remain the same. So I'll be reusing my theta parameter at every time step. And also, if you look into the dependency stuff, now if you look into the dependency of ht, so with what input it actually depends, it indirectly depends on all the inputs of the previous past, because ht is directly dependent on xt. Ht will also depend on xt minus 1 through ht minus 1, and if you go back, then it will also depend on the other previous x. So effectively, what we can say, that ht basically stores the whole information of the previous inputs into a single form. Maybe it's kind of a lossy summary, but we try to make a kind of a summary, and then we want to store it as a state, because if I want to store the whole information, it can be pretty large, which is not a very good one. So 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 that is one of the major advantage, since so one of the thing is, we whenever we have this kind of network, we try to unfold the network in order to visualize how the information is actually flowing. The advantage of this kind of network is that my parameters are actually reused, so I will have less number of parameters effectively, and therefore I will be able to train my model with more easily, and kind of it can be, sometimes it will require less amount of data as well. So this is the stuff I think I have told, so I can skip this slide. Now we can have more complex scenario. So just to elaborate it pictorially, so if you see, this is my input, and I have a set of parameters that I need for my neural network. This is my hidden state. This is my output, and this is the loss that I can compute when I know the golden value or the reference value. So this is so when I look into the neural network, this part is not required. I have just elaborated just to compute the loss. So this part will be the actual your RNN. So I can actually concisely representing a lot of information here. Now if we unfold the stuff, I'll be getting a picture something like this. We have x, we have h, we have o stuff, and every time point we are using the same set of parameters. So this set of parameters are actually will be reused at every time step. So when we look into this diagram, then it's not a acyclic graph, because I have kind of a self loop. If you look into this graph, it's kind of a DAG, so many analysis will be easier on the DAG. But in terms of representation, this is actually better because it's a very concise form. Another thing can actually also happen, like when you try to when you have a feedback from the output to the hidden state. So in that case, the thing is, you have to connect from this ot minus 1 to your ht, because this connection will be at a time point will be given in the next time point. So this kind of connection that you have to make. So another thing also to note from this diagram, like if I want to train such a model, when I have a feedback from output to the hidden node, then when I'm training, I have xt as an input I can give. I can also determine this o, and here I am actually I'll be moving I'll be giving this output in the next state. So that is the actual requirement, but when I'm actually training, my prediction for ot minus can be wrong, because when I'm training, it may not learn immediately. What I can do, I can actually feed this yt at next time point, because that is the more correct information in order to learn the stuff. So during training, we can actually feed this yt minus 1, because that label will be available. But when you go for testing, definitely you cannot feed the yt minus 1, because you do not know you have to feed the OT minus 1 in that case. So this is also a simple scenario, like when you do some kind of a sentiment analysis, uh, like you take the set of inputs and then you just compute only one outcome, and then you just actually compute the loss kind of stuff. So this kind of a sequence processing is more applicable kind of a sentiment analysis or similar kind of stuff. Now coming to another important thing, like I can have a recurrent neural network stacked upon one upon another, or maybe sometimes it's called the deep RNN. So I can have a network something like I have a feedback here, I can have also feedback here, and I can have a feedback in the next level as well. Now if I actually unfold the stuff, so I will have a dependency from this side as well as on this side. So so there can be some kind of a stacked RNN as well, but usually we do not see much layer in the this kind of a deep one. So maybe 3 to 5 layer maybe you can see, but you will not see a kind of 100 layer deep in that kind of stuff, because when you do the unfolding, that actually creates a lot of complexity. Like when you have CNN, it's just a simple propagation one after another, so you can have a very deep network. But in case of RNN, you will not find a 100 layer deep of hundreds, a stack of 100 RNN layers, because that will be too complex, because you always do some kind of an unfolding with respect to time. That time the depth actually increases. To formally introduce the recurrent neural network or the vanilla RNN, so we will represent the network in this diagram. So we have the input, we have some output, we have some hidden state, and we have the set of parameters. So so the in terms of the functionality wise, uh, you the first of all what we do is you take the x and ht minus 1, that will decide the pre-activation value, which we call as at. So which will be a function of ht minus 1 and xt with some parameter stuff. And then on at we'll be applying some kind of a activation function. In most of the time the tan h will be used as your activation function, so effectively I will get ht. Now this ht will be used to determine the final outcome, the yt. So we have another set of parameters, and uh, so here the input and output have the same length. So now I will elaborate with one examples that I have taken from one of the websites. So there's a famous guy called Andrij Karpati. Many of you have heard his name already. So what he has actually developed an interesting example called a character RNN. So what he does is he takes a single character as the input, and he will try to predict the next character. So in this example, let us consider we have only 4 characters. So we encode H with 108 encoding. So the first position basically denotes for H. Similarly, second position will denote for E, and so on and so forth. Now, when I give this H to hidden state, this hidden state will compute something, and then it will predict the probability for the output. So this is a kind of a non-normalized probability, because these are not between 0 and 1. So you can actually apply the softmax and you can get the stuff. So in this case, it's supposed to predict the E, but it will actually predict the O on the last character. So which may be wrong, but this is the way it will work. Like it will take the encoding, it will take the state, and then it will compute the outcome, and it will update the next state. So that is the thing. In the second time step, it will get E, and it will interact with this state, and it will probably predict something else. and it will keep on doing so. And every time, whatever parameter you have, so this WHH or WXH, so HH means the parameter with respect to hidden layer, and XH is the input to your hidden layer. So these parameters will be actually reused at every time step. And then, so if you can train this such kind of a network with some kind of a data set, and then you can start predicting the next character. So this guy did a nice experimentation. So what he did, he basically trained a similar kind of a network, the character RNN, not the vanilla RNN, with some a little bit advanced stuff, and then he start predicting the next character. So he trained with Shakespeare writings, and then it start predicting the kind of text that Shakespeare can actually write. So it created a similar kind of a text that was there in the Shakespeare writing. Another interesting thing also he did. So he took the LaTeX code of some maths book, and then he trained the character RNN and stuff, and then it start predicting kind of a next character. So it started predicting some kind of a mathematical text. So these are kind of a generated text, so this has no meaning, it's absolutely wrong. But the first impression is that it looks like some kind of a perfect mathematical stuff, like it has lemma, it has proof, it has probably learned something. Like you have lemma, you give the proof, then lemma will have some kind of a number, and so on and so forth. So this is also again from the latex stuff. He also trained the model with Linux kernel code. So so he took the whole kernel code and then trained with this character RNN, and then it generates a code something similar to a C code. So these are actually generated code. So if you look into this stuff, so it's actually a C code generated. It's actually a bogus code that does not do any good thing, but the first impression will be definitely that it's a perfect C code. So it, at least it has learned the structure, how the language looks like, or how what is the actual format of that stuff. So so in that sense, the RNN is a very powerful tool because it can learn a very complex structure, so that at least we can see from this character RNN. So the good part of RNN is that it can process any kind of a length, so which is one of the good thing. And so it can actually use the information from the distant past, at least theoretically, but there are some challenges. And the important thing is that your model size does not increases for a longer input, because if you even if you have a longer input, you'll be using the same set of weight parameters. So the weight parameters are actually shared, so which is a good part for your RNN. The disadvantage of RNA is that computation is actually slow, because when you actually unfold, or when you have to unfold a large number of time step, in that case the system can become slow, or the training process can become slow. And if you have a long-term dependence, in the example that I have shown in the very beginning, like i I born in Bengal, I grew up in Bengal, and then I, after some sentence I write, I can speak fluent Bengali, so that Bengali will be kind of related with the sentences, but it can be from a distance past. So so sometimes it becomes difficult to access that information from a past history. So there are some mechanisms through which we can actually overcome. So we'll be looking into that stuff. So now one of the thing is, when we have this RNN, since it has a feedback loop, and we know that if we unfold the system, then probably I can see a directed acyclic graph. Now, the main concern is how we can actually learn these weight parameters, because that is the most critical thing in any kind of a neural network. Because if you have the good set of weight parameters, then your system will perform well. Now, the main question is how we can learn these weight parameters, because we have some kind of a feedback loop. So it's not a very complicated, but it's not a traditional back propagation. You have to handle with differently. So if you look into this diagram, like I have unfolded an RNN over the time step, and every time step I can actually compute some kind of a loss, and then I can actually compute the total loss out of that stuff. So now once I have this loss, I can actually do a back propagations on this network with some modification on the back propagation side, or just to take care of the things like that this set of parameters are actually shared. So that is the additional constant that we have to take. Like, just the one of the thing that I want to highlight, like if you look into these weight parameters, then these weight parameters actually control the loss one through this path, and this weight parameter also controls the loss through another path. So I have to take care of all the paths that are possible in which the information can propagate. So I have to take care of the all the path through which it has some kind of a influence. That is the main challenge here. So once you unfold, uh, you have all the paths, and only thing, all the, for this set of parameters, since it is shared across the time step, you have to take care of all the gradients, and then you have to sum up. So that is the main thing that you have to take care of. So I will give you a very simple overview. I will not go into the detail of that stuff. So if you have this kind of a network, so one of the issues that you have to take care of is the number of stages that you want to consider, that you have to decide. The number of stage means how many times you want to do the unfolding. So that is the thing that is required, because I can have a network in which I have an input length of say 600. So in that case, I may need to unfold 600 times. So which may not be suitable. So I have to choose some kind of a number of stages for which I want to do the unfolding. So that also acts as some kind of a hyperparameter. And the issues that we will face, like when we do this unfolding for a large number of time steps, then we can come across with this kind of problem. So vanishing gradients and exploding gradients, I will come back to these 2 points after a few slides. So the loss that we actually compute, we can actually compute either through mean square error. So this is the error at a single time point, and this is the total error over the unfolding time horizon. So tau is my time horizon over which I have unfolded my RNN. Also, you can actually compute the loss as a classification problem. So you can cross entropy loss, that stuff that you can actually compute, and you have to use the truncated back propagation through time, or the back propagation through time kind of approach. So you unfold the stuff and then you do the back propagation. So one of the thing is that in many language problem, you will be finding that your input length is very high. So maybe it can span 1,000 words or maybe more than that. So typically what is being done, so even if you have a large input, uh, what you do, you just restrict the unfolding stage, let's say 100 or maybe 200 or maybe 50. So not a very large number. So every 50 words you do the processing and do the back propagation, and then go for the next 50 words, and so on and so forth. Because if you want to look into the whole say 1,000 words, then probably it will be difficult to learn because of these issues. So I just wanted to give a very basic overview of the gradients, not the exact back propagation. through time. But just to give you the flavor where the complex from, if you can understand this, probably you'll be able to extend it for the RNN as well. So in a simplified way, I can actually express the dynamics of a RNN in this way. Like I have my hidden state, which will depend on xt and ht minus 1 and a set of weight parameters.
Yes.
And at a given time point OT, the output, which will depend on some hidden state and some kind of a weight parameters, and that may be related with some other kind of function g. So this is the basic dynamics for my RNN, so in a simplified form. So now, so once you have this output, you can actually compute the loss over a time horizon tau units. So this is the loss at a given time point, and you just sum up for the overall the whole time point, so you will get the total loss. Now the thing is, the main important thing that you have to compute how this del L del WH actually can be computed, because I have to determine the new set of weight parameters. Now del L del WH can be computed in this manner by applying the chain rule. So my L is nothing but this expression. So I can actually put this stuff by replacing, I replace the L with the actual thing here. So which will be loss at every time point sum over all the time horizon. Now this loss actually, so we can apply chain rule. This loss actually depends on the OT, and this OT is nothing but the function g. So how g actually depends on ht, and how this ht actually depends on wh, so that is the dependency, so that you can derive from the chain rule. So this is the expression that we get for del L del WH. Now the point is how we can actually compute this term, because HT is an intermediate state, WH will be shared across the different time point. So this is the main challenge that, or the main thing that you need to know. So the computation of this is as not trivial. So what we have to do, you have to compute this thing in a kind of a recurrent manner, because if you look this ht, this will depend on your this will depend on your wh. So it will depend directly on the wh, and wh actually influence ht minus 1 as well, because of the from the previous time step, and that ht minus 1 also influence your ht. So if you look into the computational diagram, you will have a dependence in this manner. So effectively, what you have to do is you have to take the derivative of f with respect to wh, when f is directly a function of your wh, and the other way is how f actually varies with respect to ht minus 1, and then how ht minus 1 depends on wh. So this is the expression that we have to compute. So this is the main thing. Now if you look into this expression, if I say this is my at, and this expression as my, let's say, bt, and the first term here I say let's it's as a ct, and the last term that we have, we can actually say this is my at minus 1, because these two terms are somewhat similar, only thing here I have suffix t and here I have suffix t minus 1. So effectively I have a very simpler expression. Probably I can write at equal to bt plus ct times at minus 1, so which is somewhat a simpler form. Now we can actually express in a closed form expression by expanding this stuff. We will be getting an expression something similar to this. So there will be kind of a product term that we will achieve get, and there will be a sequence of additive term as well. So here in the simple scenario, I have a product of C. Now, if you look into the real RNN, then this will be a product of some kind of a matrix of the W weight matrix. So, so when you have this product of W matrix, or even if it's a scalar, if these Ci values, Cj values are less than 1, then if you multiply it multiple times, then the value will be much smaller again. Effectively, it will get vanished. And if Cj are greater than 1, then your value will start exploding. So that, because of which we get the vanishing gradients and the exploding gradients. So here it's we look into Cj because we consider different value, but when you have this RNN, it will be the same value that will get multiplied. So effectively, now once you have this kind of a expression, you can replace the original expression for AT, BT, and all those stuff. So you will get more scary equation, but it's very simple thing, nothing great as such. So this is the main challenge. So here we have just looked into only one of the weight parameters. Now if you have the proper RNN, you have to compute for each of the weight parameters. So we have seen we have W, we have U, and we have V, three set of parameters. So you have to compute in a more similar manner, but this is the main challenge. So I'll not elaborate much on that front. The issues that we actually face here, when that I have already told, like when I propagate the gradient through this red path, every time it will get multiplied with this W. And if I unfold for a large number of time step, then W will get multiplied every time. So since it's a matrix, so effectively the largest eigenvalue will determine whether the value will get explode, or the or it will get vanished. So if the largest eigenvalue for W is more than 1, then I will have a explosion in the gradients, and if it is less than 1, then I will have a vanishing gradients. Now, if you have the explosion of the gradients, then there is a way that you can do a clipping on the gradient. So let's say my gradient crosses 10, then I can clip it to 10. But if it is a situation when the gradients actually vanishes, I don't have much option to play with that stuff. So that is one of the issue in the vanilla RNN. So this is the basic RNN on, sometimes it's called the vanilla RNN as well. So the thing is, it's hard to retain information in the hidden state because you have successive matrix multiplication, and these hidden states of recurrent networks are inherently short term because it can store only a small information only for small unfolding scenarios, or for small time step, small number of time step. So so we need some mechanism how we can actually retain that information for a longer time. So that is the main challenge.
So,
Now in order to overcome that stuff, so people have proposed many other advanced architecture. So two are most popular. So one is the LSTM and the GRU. So LSTM means the long short term memory, GRU is the get and recurrent unit. So I'll elaborate that step. So the main idea here is that they actually use some kind of a analog gates to control the propagation of the information. So how it is being done, I'll be elaborating. So just to visualize how this RNN and LSTM actually fit in the RNN stuff. So so GRU is exactly the similar kind of stuff as RNN, but with some more advanced architecture. LSTM will be more advanced, and it has some additional information. It has addition. It requires to store additional thing as well. Now, in the literature, if you see, the LSTM was proposed earlier, and since LSTM is more complex architecture, after that people actually propose GRU because it's less computation intensive. But here in this lecture, we'll first try to see the GRU architecture, then we'll go for the LSTM. So, so let's look into the stuff. So, what GRU actually does. So, and how this control of this propagation of information that can be controlled. So, when we have this vanilla RNN, we have this HT minus one that is getting propagated to HT. So, that was the main stuff. Now, here we actually provide a few kind of a gates. Like if you, I hope everybody is familiar with marks. Like we have some kind of a control gate. If my control is one of the path will be chosen. If the control is something else, the another path will be chosen. So here, similar to that stuff, here if ZT is 1, then this information will propagate. And effectively, if ZT is 1, this path will be 0. Effectively, no information will propagate through this path. So that is the kind of additional thing they have actually introduced. So we have some kind of a gate that actually controls the propagation of the information. Now, here, here we would like to see this stuff. So let us consider this HT minus 1 is the kind of clothes that I wore yesterday. And let's say XT basically represents some kind of a weather for today. So this is the clothes that I wear in the T minus 1 day. And this is the clothes that I planned. I a kind of a candidate clothes that I want to wear for today. Now I can make some kind of a analysis or dependency, like if the weather is bad, maybe I can choose the previous day stuff, or if the weather is something else, I can choose this stuff. So I can actually decide depending on certain kind of thing. So what I put up yesterday and what is the current weather, based on that I can actually decide what dress I will put up for today. So this kind of gate or this ZT that is being computed based on your XT and HT, that computes some value ZT, which basically decides how much information will propagate. So ZT will not be just like a 0 1, something similar to your marks, but it value will lie between 0 and 1. So it it basically gives how much information it should propagate. So that is the kind of additional control that is being provided. So ZT is called the update gate and RT is the reset gate. So by looking into the current weather and by looking into the dress, I can actually reset certain things and then I can choose the final step. So how much I want to reset, how much I want to update, that can be controlled, that can be learned from the actual data. So it's giving some kind of a additional control to propagate that information. So these are the actual mathematical stuff. So I will not elaborate, and I think I have actually explained the whole stuff. Now, so this is the simple GRU. The LSTM actually is a more complex stuff. So which basically have a combination of both long term and as well as the short term memory. So the hidden state, the HT, will be kind of a short-term memory that will store the cell state, the CT, that at least we have seen in one of the examples earlier in the diagrammatically. So that will store the long-term stuff. So and there will be a set of gates through which we will be able to control the propagation of the information. And interesting thing is that leaking between the short term and the long term memory is actually allowed, because then we'll be having more control over that stuff. So if we look into the LSTM architecture, so we have this HT, something similar from the vanilla RNN. Additionally, we have this cell state CT and CT minus 1. And this is a some kind of a gate that controls the propagation of the information. So F is known as the forget gate, input gate, candidate get, probably I can say, and OT is the output get. So all this basically denotes the kind of a control stuff. So how much control you want to propagate through that path. So if you look into this thing, so there is a way from HT the information can pass to CT. Even there is a option that from CT,
Hello.
there's a lot of control, so it's kind of a computationally very expensive, but it actually performs very well in terms of the long dependency. Another major thing is that like the vanishing gradient issue can be overcome in this network either in LSTM or in GRU, because when your gradient actually propagates through this path, then there is no direct influence of any other thing. So this is a situation when where the information will be propagating from two paths, so we have some kind of a addition. Earlier, when we have the vanilla RNN, we have the information that is getting multiplied every time. In this case we have two paths through which the information can get propagated. So if one of the path actually contributes, so that path will have the high gradient. Effectively, I will not face much of the vanishing gradients in this case. So that is ensured to some extent. And these are the detailed functionality, but I will skip because that is not very much required here. And if you look into the literature, you will find many different variants of diagram for LSTM. This is just for your reference. All are actually similar, but they try to visualize it in a different manner. Now I will come into few of the applications quickly. So let's look into this problem. So let's say I have to fill the next word, or I have to fill some kind of a blank. So here I am dash. The second sentence is I am dash hungry. Third sentence, I am dash hungry and I can eat a full tandoori. So if you look into this stuff, so for the first sentence, probably I can say I'm happy, which may be okay. For second sentence, I can say I am not hungry or I am very hungry. Both are actually fine. For the third sentence, if you look, then probably I can definitely say that not is not basically is incompatible, because if I say I am not hungry and I can eat full tandoori, that brings a kind of a conflicting stuff. So definitely I cannot put not here. Now if I want to predict some word in my sentence, then I have to look into the whole stuff. So this word is not dependent only on the past but also on the future input. So I need to have some mechanism where I will be able to see the past set of words as well as some future words. Based on that, I should be able to predict that thing. So in order to do this, what people have actually proposed called the bidirectional RNN, unfolded over time. So which is our traditional RNN, and we have another stuff like on a RNN. If you look into the red one, then it is information is flowing on the backward direction, but still it is a kind of a acyclic one, even if it is the bidirectional stuff, but it is an acyclic one. So what it will do, it will look into x1, it will compute h1 in the forward direction, then it will compute h2 in the forward direction after looking into x2, and so on and so forth. Once it hits to xt on the at the terminal stuff, it will compute ht minus ht in the backward direction, and it will compute whole set of h in the backward direction. Then these two h's will be combined to predict my o1. So effectively, after that I will be doing the normal stuff, but it has to look into the whole, it has to go through the whole sentence, it has to come back to the whole sentence again, then it will be able to predict this one. So effectively it depends, this o1 will depend on from the forward side as well as from the backward side. So if I have this kind of model, then it will be easy for me to predict this word, because otherwise, if I look into only the past words, then my prediction will be not very accurate. So this is one of the major applications of RNN. The second is machine translations, the encoder decoder kind of stuff. So let's say if I want to translate some English statement to Kannada, then what I can actually do is uh, uh, I look into the whole sentence, and when I look into the sentence, I keep on updating my hidden state. And once I hit the end of sentence, I create some kind of a context vector, and then I give the context vector to for a decoder stage, and the decoder stage will start predicting the some kind of a output for that stuff. So what is the main point here is, like, whatever input I am taking, I I'm creating some kind of a hidden state, and eventually I'll be creating some kind of a context that actually summarize the whole stuff, whole input. And then I give this context to my decoder, and it will start decoding the kind of thing. So this is also a very good model. Many times it's actually applied in machine translation, but the issue that can be faced, like when we are predicting for S1, we are just looking into the context vector and then we are predicting the first output. Then when we are predicting for S2, we are looking into this one and S1, and we are predicting certain stuff. But the thing is, then the dependency from this context and S2 is gradually increasing. So context to some output will be increasing. So in order to improve the performance, what we can do is that we can create some kind of a context for each of these stuff. So here I have only one context that is getting given to the decoder, but if I can create some context C1 for this guy, some context for C2 for this guy, and so on and so forth, and C1 depends on the whole stuff, C2 also depends on the whole stuff, then probably I can actually improve the stuff in a better way. So that is the actual idea for your attention. So where you have one forward path that uses the bidirectional concept, and one backward path similar to your bidirectional. And once you have these values, you basically compute some kind of a context, and this context will be having some kind of a weightage. That weightage will be determined by another neural network that you have to train, and this neural network output, which is alpha t1, that will tell how much weightage you want to give for a current stuff. And for every st, I will have some kind of a context vector or the context situation, so based on which I'll be detecting this yt. So if I have this model, then my context will actually vary at every time step. So sometimes I can give more weightage to the second word, sometimes I can give more weightage to the last word, and so on and so forth. So effectively I can provide some kind of a attention to the appropriate location of my input. And these are some of the other kinds of problem that also you may come across. Like if you go for image captioning problem, then you what you have to do is you take the image, you extract the feature through some CNN, and that feature will be the input for your RNN. So that will be the initialization of your RNN, and then the RNN will be applying and it will start predicting some kind of a caption for that stuff. So here the thing is you extract the features from the image and give it to RNN. The RNN will start predicting the next the appropriate word for that. And so you have to train and then probably you can go for the actual testing. So these are some examples when your image captioning can perform pretty well. There can be issues when it can predict very badly as well, because uh, something it might get some wrong impression, and then based on that it can actually predict wrong caption as well. Visual question answering also another important problem. So you need to extract a set of features for your image, and you need to analyze the questions through some kind of a RNN, and then probably you have to combine these two stuff to predict the actual thing. So if you have some image, you extract the feature or some kind of a embedding on the image, and you take the sentences and try to embed the sentence in some embedding form, and then you analyze the whole stuff and start predicting the thing. So basically if you have this visual concern answering, so I need two threads effectively. In one path I'll be predicting, I'll be extracting the feature from the image. In another path I'll be extracting the feature for my sentences, and then I'll be training some model, and then probably I'll be updating the whole stuff. So you can do whole stuff together, which is fine, but only thing you need two separate paths. In one path it will be a characterization of your image, the other path will be analysis of your language. So I think I'm running out of time. So in summary, so RNN is good for modeling the sequence relation, and so it's basically does through some kind of a recurrence relation. The good part is that it can handles the variable input length, but the basic issue is that you can have vanishing gradients and the explosion of the gradients, that issue. So you can use LSTM on the GRU based architecture in order to improve that stuff. And when you try to train such model, backpropagation will be used, but you need to take care of few of the other stuff. So with this I will stop. Maybe I can take questions now. I think I'm running out of time. Hello, am I audible?
Yes, sir. You are
Okay.
audience. Do you have any questions, sir? One question. Hello, sir.
Yeah.
I like the analogy of saying that clothing in the GRU. Is there any some kind of analogy for LSTM on the three gates like output, input, and forget gate?
You can extend it. Right now I cannot give you that analogy because LSTM is more complex network. So similar, if you introduce more control stuff, probably you will be able to say in a similar manner.
Okay.
So when I have a dependency, I can model it in that way.
Okay.
So
Like the
I
forget. What is the main use of that forget gate from the, which is coming from the short term memory or long term?
forget get is to for it's coming from the from your long term stuff. Sorry, forget get is you're coming from the in your CT path. So this FT will basically guide whether you want to forget the distant past or you do not want to forget. So
Okay.
So one of the important thing that I have not said, this ct minus 1 or the ct will be some kind of a vector,
Yeah.
because you'll be carrying a lot of information through that vector. So for some for some of the component you may forget, for some of the component you propagate that information.
Yes,
So
sir.
if
Capturing the long range dependencies, right? Like,
sorry.
for means the main use of this LSTM, that long memory is like to capture the long range dependencies.
Yes, absolutely right.
Okay, and on one slide you talked about neural machine translation, and also with attention, right? Um
Yes.
there, the before slide you said from English to Canada.
Yeah.
I also did one similar project where converting from English to Telugu. One of the problem for this Telugu language is like, uh, while there is more vocabulary words in Telugu when compared to this English and any another Tamil or Kannada language, there are some means you will find more words similar with those similar vocabulary. What I'm like, there are some mismatches and I'm not able to translate for this Indian languages. What is your suggestion?
See, this kind of network actually has to be trained with large set of inputs. If you have a very limited set of inputs, it may not learn. So you can use some pre-trained model from somewhere, so that you do not have to train the model. So that can be one of the possibility. Otherwise, if you try to build from scratch, then you need good amount of resources and good amount of data. Otherwise, it's really very difficult.
Yeah. One of the text like pre-processing step is like you want to limit the vocabulary in two languages. Like you want to limit the vocabulary to 10,000 language, 10,000 or something. In Telugu, there are, for my data set, there are many vocabulary. If I'm clipping that vocabulary, then I'm getting low performance. If I'm leaving it also, I'm getting low performance. That kind of issue I'm getting. Maybe I will try to increase the data set and clip like I will try it.
Yeah, increase the data set, and maybe you increase the model size also. That may be required, because you need a very bigger model.
Okay, sir. Thank you.
We will, sir. There is one more question on the chat box.
Yeah, so how do you visualize what RNN has learned? Yeah, so there are few methods that can be shown. I don't have any slide immediately, but what I can actually say, like the character RNN that was predicting the next character, that example. So if you go to that blog, you will find something for that. One of the thing is, like when I'm predicting the next character, let's say I can predict a few set of characters. Let's say I get H, then probably I'll be predicting E for my hello. If I considering hello is the word, then I along with that I'll be predicting some kind of a values for the other character as well in the example itself. So that probability can give me some kind of a confidence value, that whether I'm predicting with high confidence or with low confidence. So that can be actually visualized. So what uh, uh, with what confidence I'm actually talking about. So I would recommend you to go through that blog. It's a very interesting blog. You will have some idea for that. So that is with respect to that one. And in case of attention, people have also attempted, like whether it is, what does the actual attention means. So they have observed that the important word will have higher weightage. So if you see this one, so sometimes you will be getting large value for alpha t3, sometimes you will be getting large value for alpha t2, depending on the scenario. So that actually indicates that it has actually learned uh, to which what it has to give more weightage. So that is also people have seen.
Uh, I
Yeah.
think there is no more questions, sir. So
In the chat, sorry, I can see a few more questions in the chat box. Just let me just go through quickly and I will finish. So for weather prediction, is it possible to use LSTM to predict multiple consecutive timestamps? Yes, it's absolutely true. Like to predict some feature like temperature, humidity, etc. for consecutive 3 hours. Yes, you can do that stuff. Yeah. So I think there will be a session by Professor Jimchon Mathur on the deep learning and the time series. So you will get to know all of those stuff. Yeah, I think I can stop now probably.
thank you very much, Arjit sir. So
Thank you.
your talk was very informative, like on the sequence modeling using recurrent neural networks. So a lot of you have highlighted the most important part of the recurrent neural networks. So I hope the audience would have got a lot from your talk. So once again, thank you very much, sir. So I think we can close this session.
Thank you. And I'm signing off.
Yeah, thank you, sir.